Let's go ahead and get a feel for these orthogonal complement spaces. So let's let a W equal to the span of a set of vectors, say W1, W2, all the way to Wm. Let's let this be a subspace of Rn. What we want to do is we want to characterize what W perp looks like, what the orthogonal complement looks like. So let's try to characterize the orthogonal complement of subspace W. So what we're going to do is we're going to take an arbitrary element in the orthogonal complement. Now, what do we know about this? We know that every vector in the orthogonal complement is orthogonal to every vector in W. Okay? In particular, all of these vectors, and only all of these vectors, are going to be orthogonal to every vector in any spanning set of W, including our spanning set here, W1, W2 to Wm. Okay? What that means is we kind of get a system of equations. We know that the dot product between W1 and our arbitrary vector x in the orthogonal complement, and W perp, is going to be 0. That's what it means to be orthogonal. But also W2 dot x equals 0, and so on. X is orthogonal to every vector in the spanning set, and therefore every vector in the span. This kind of gives us a system of equations. Any vector x that satisfies these equations is going to be in W perp, be in our orthogonal complement. Okay? So what we want to do is we want to kind of play around with this system of equations. Now, we have lots of dot products here. There's another way to characterize dot products so that it's matrix multiplication. You may recall that if I have the dot product of two vectors, that's the same as taking the transpose of the first vector and matrix multiplying it with the second vector. Okay, this is exactly the same as a dot product. And let me just show you why, right? If I have 1, 2, dot 3, 4, I get 1 times 3 plus 2 times 4, just multiplying the corresponding components, so I get 11, right? Now, do the same thing, but now transpose that first vector, and now do matrix multiplication. Okay? This row and this column, I take the dot product of them. I get 3 times 1 plus 2 times 4, and I get 11. Okay? So that just shows, as an example, that the dot product of two vectors is the same as the transpose of the first times the second. And that's exactly what we're doing here. Instead of looking at the dot product, we're taking the transpose of the first times the second. Okay? And I could do that for every dot product equation here. Okay? Now, whoops. Lose the dot. This is no longer represented that way since I took the transpose. This is just matrix multiplication. There we go. So now if you've done lots of linear algebra, you might look at this and say, well, wait a second. This looks a whole lot like a matrix vector product. Okay? In particular, this is exactly what we would get if if we take the matrix where the rows are these guys, so W1 transpose, W2 transpose, all the way to Wm transpose. And then I take vector x and I get the 0 vector when I'm done. Okay? Means exactly the same thing as I have here, because when I multiply a matrix with a vector, I go row by row and take the dot product of each row with this vector here. So W1t with x equals 0, and then do it for the next row, and then the next row after that. Okay? So any solution to this system is going to be in WPerp, right? Now, this is a homogeneous system of linear equations. The solution to this set is the null space of this matrix. Okay, so let's give this matrix a name. Let's call this matrix A. Okay, and then what we are observing here is that, first off, the row space of A is exactly equal to what W is, right? Because W is just the span of these guys. These vectors are the rows of the matrix. Okay? So note W is the row space of A, and the solutions to this system are the vectors in WPerp. The solutions to this system are exactly the vectors that are in the null space of the matrix. Remember, the null spaces are all the vectors that solve this homogeneous equation. Okay? And WPerp is equal to the null space of A. That is, more generally, row space of A perp is equal to the null space of A. And what this does is it gives us a way to find, to characterize the orthogonal complement of a vector space. If we know a vector space can be expressed as a span of a set of vectors, if I take those vectors and use them as the rows of a matrix, and then find the null space of that matrix, the null space of that matrix is going to be the orthogonal complement of the original subspace.